What we have here is probably going to be something that looks more like a jumbled mess than anything else. So your board may start looking something like this to begin with. And what we're going to do is we're going to isolate the key components that we actually need. There's a few things that we're going to need to do today. Some of that is going to involve our thread. So thread is very, very important in this lab. We will have a statics block here, and then we will have a couple other options where we're going to use some of this inclined plane in order to understand how different forces in different directions come into play. So a couple things we're going to do. One is we're going to start by cleaning off the board as a team carefully, and we're going to see which components we actually need to have in place so that we don't just have a cluttered mess at the starting point. So we're for sure going to need a couple of these, at least one for now, and we aren't going to need our force wheels here. We will need a couple of these guys. So one we can just sort of leave down below, out of the way for the moment. We are going to need our inclined plane. One thing you'll notice is you may have to remove the securing tape so that your incline is not always at 90 degrees 100% of the time. So we will be able to measure what our incline is. So we're going to measure at some different inclines. We're going to do a few different things at the same time. So this is going to kind of come off to the side a little bit. And we'll set a few different angles, something like 10, 20, 30, 40, 50 degrees, and so on. And we're going to run that through a couple different directions. So part of what we're trying to understand is at the outset, we're going to try and set this up so that it's in plane. So we'll set at our 10 degree, we'll set this up. So very, very close, set it right at something like 10 degrees. We're going to take a look at our alignment across this plane to see if we're going to have the string dragging or not. It needs to come up slightly. And what this will do is this will allow us to have the string fairly low, but not actually dragging against the material, so we don't have additional friction to worry about. And then you see we have this handy dandy force scale that we can use. And so long as we've been careful with our placement, what we can do is we can leave this longer because we're going to need a little bit longer mechanism for when we add in pulleys and start changing directions and all of those sorts of things. If we want to pull at some different kind of angle, there's a couple ways in which we can actually do that. So we may also use the balance beam for some parts of this. We also have a couple larger, at least one larger pulley already configured, and that will change also some of what's happening as far as the force that we actually observe. So this spring scale will tell us how many newtons are being applied, and one of the mechanisms is going to be with our foam block, and we have felt sides, and the felt sides are going to be what we're using to connect this string. So I can already tell this is going to have to come up slightly. Somewhere along this plane is pretty close. So our felt blocks are enough that we're going to see how we overcome the friction and what that sort of force is as we pull directly down. So we'll have to change and make sure that this is in alignment and not pulling at a strange angle initially. We want to make sure these things are as vertical as possible. Then you can do a lot with the actual measurements. So we're going to connect up the thread and show an example of a few different mechanisms by which we can make some measurements. And then we'll take a look at how we can look at a measurement from a distance or a lever arm to apply to some of these things. We may look at a couple other options as well as far as using hanging masses, because this is going to tell us something about how frictional forces are applied and what they mean at different angles. Then we can also look at how we can hang some of our masses, and we can say, okay, based on what we have available here, if we had a 50-gram mass loaded up and we were running this instead of our tilt scale, if we were running, for instance, we were running this way, where we had our scale, and we could do this a number of different ways, including we could even have it turn twice, something like this, with a close spacing. We can set it at a distance. We want to know at least that these are roughly on the same level, and they're close, not quite there. That's a little better. So we could measure this way and say we have our thread running up through here, down through here, and up into our spring scale. And so what we would see is this kind of effect. So we're going to go ahead and thread our string. We're going to do some things here with just the hanging masses, and then look at the sled block as well, and start to get a sense of how the forces in the different directions are actually adding up and why they change with such regularity. So here are a couple quick examples of what we're going to be looking at, and it's actually going to be a little bit more beneficial to use our degree wheel. So some of the things you want to pay attention to in your setup as you're configuring these boards, because you'll have to assume that your previous neighbors left them incorrectly. You want to set up something that gives you enough length that you can move things around. You can also attach two of these boards together to work with a team and give yourself a little bit more working distance to do some interesting things. So you want to start with something that, if you're measuring just the angle downward instead of getting any kind of pulley multiplication, you can see what's happening if we bring something all the way across. And we have, again, our level bubble sort of dead center. We want to have 180 degrees, meaning fully horizontal to our string and our load, right? And so even if this is moving up and down, you can see it's still on those same angles, and the first one at 90 degrees. And we want to look at what the force is. So in this case, we have just a little bit more than 0.5 newtons. So this is about 0.65 newtons, because it's right in between two of the smaller markings. They also have millimeters on one side and then ounces on the other. So you can keep track of which ones you're using. You want to use the same consistent units as you're taking measurements to go along. So you're going to change the angle of this reading and see. Let's pop on over here to 60 degrees. And again, you want to make sure that this makes as much as possible a straight line all the way down your measurement line, so that you're not measuring an angle at an angle, because then you have two angles and not one. So at 60 degrees, does this change? Yep, sure enough, this is right at about 0.6 for this particular instance. And you can add mass, and you can do all sorts of other things. You can take a look, if you can get it to go far enough, you can take a look at a completely horizontal measurement like this and say, okay, if there's no additional load being taken up, what is the completely horizontal measurement? A little bit less than 0.5 newtons. And if we change this around to be a much steeper angle, what do we get? And so this one appears to be 0.5, 0.6, 0.7, almost about 0.75 newtons or so. So same mass, given different angles, what we're going to do is measure how those forces come into play, and we're going to figure out what some of the forces are interacting on these pulleys and angles. Then we're going to do the same thing by switching over, and instead of using our weights, using different weights, different angles, we're going to switch to our sled, and that's where you might need the second one, give you just enough room to start playing with. You might need the second one in order to figure out, okay, at 10 degrees, at 12 degrees, what kind of frictional force is coming into play, and where is that frictional force sort of more easily overcome, at what angles, and how do some of those things change. So this is what we're going to be doing, and you guys can play around with additional lengths of each of these. And so you want your final measurement, whatever series of measurements you're taking, you want your final angle to the measurement device to be measured by your degree wheel. So even if, for instance, this is too far up and we need a little more distance because we're trying to get this lined up where we're making some fine tuning here, and we want to bring in our additional pulley, but we want to do so in a way that introduces deflection. What we want to know is when we introduce that deflection, how far down does it come, and how much does that angle impact our end result. So how far down does this change, and what's the net impact? And so by trying to keep everything in alignment, you're going to not have too many issues as far as friction against the face. The friction is going to be very minimal. And you're going to see, okay, if we change the incoming angle, then does that do the same thing as changing the measurement angle? So in this case, we're just a little bit below 0.5 newtons. So when we were up here, over around 30, about 45 or 50 degrees, whatever we were at, about 40, 50 degrees, about 40 degrees below the 180 horizontal here, we're right at about the same force that we were at this angle. But these are things that you want to start testing using a bunch of different angles and figure out what angles are involved in order to know what the forces are for each of those angles. So remember how to use the force times your trig function, and that will give you what that effective force is for that particular angle or that component of the force. This is just a really great way to be able to visualize that in a way that, so long as you're keeping things level and understand where the horizon is for each of these, it'll make your life a little bit easier in terms of being able to operate how these work and use lots of different angles to make some interesting measurements. So here we have a block arrangement that we're going to do a couple things with. For setup details, things that you want to note are you want to make sure that this angle at about 10 degrees matches up with the 180 plus 10 degrees. You're not actually interacting with any of the other components. You're right at about 190 degrees, and then taking a measurement maybe at 90 or some other angle consistently. And then you want to see, as you detach this, as you detach your force measurement, you can watch as you're pulling it, you can watch what the level sits at. So in this case, pulling it up this incline at 90 degrees, you hit somewhere on the order of, on the friction side, about 0.3 newtons or so. I'm trying to be careful with the magnetic arm there. So it's helpful to have someone watching the scale on your team as you're watching what happens, the difference between the smooth block side and the friction side with the felt pads. So the combination of these gives you a different angle. You also want to look as a control at the angle that you're going to pull at. So if it's a 10-degree incline, you want to be pulling at a 10-degree angle in order to get no additional bias. So here it's a little easier to see, right at about 0.2 newtons on the friction side, maybe about 0.18, or on the friction side. Again, you want to keep the string looped up and underneath the small disc. Here we go. So we can keep track of the angle, make sure that we're consistently at 10 degrees. Have a friend keep you accountable at 10 degrees. So this friction side is just a little bit higher, right at about 0.2 newtons instead of 1.8. So you do the same thing. You measure at some additional angles. So you can measure at what would be a 45-degree angle going the other way, and so that'll be the difference between 190 and 45. So this one would be 145 degrees, which will be here. So that difference should be right at about 145 degrees. So that 45-degree angle should give you information as to how much force it takes. And so to get it to move consistently and smoothly, you're somewhere on the order of about 0.35 newtons. On the smooth side, for the felt pad side, you're closer to about 0.4 newtons. And that's what we're trying to look at, is some of the differences with these different angles. You do the same kinds of things at a few different angles on these parts. You can make them more tortuous. You change the angle of the incline as well as the angle that you're pulling at, and you look at what the forces are at those different angles and see if you can make the math make sense by back figuring using the trig, so the trig function times this force, and that gives you, for a given angle, what the x and y components are going to be of each of these forces, so that you can figure out whether or not that makes sense. Should you expect it to be greater or less than based on math instead of guessing?